All right, it's alive. Okay, I'm making my screen a little smaller now, my window, which makes it zoom. So hopefully that'll be better. Feel free to point things like that out. Okay, I made this video before. This video is, you know what it is, right? This is Information Theory, Episode 3, the Apophenia of Mathematics. And how we can overanalyze. We're going to go through the randomness notebook. I've changed a little bit. Now, I made this video once. You don't want to hear my woes, right? But I made this video once and lost the audio. So I'm going to go through this. Might even be bugs. I usually work on the thing and do a run through before I go. And I had done that, but I didn't do it again. So we'll see. Sometimes we have a thing called bit rot, which is where things that are left no longer work. So that's okay, because then we'll just fix them, right? Okay, let's make sure all the output is clear. Okay. So, all right. Now, let me explain again what's going on here. Okay, what you see down here, this is what you call ordinary Python. In any Python, you'd see this. This is import the NumPy package or module. Let's call it a package. And I can say as NP, this makes NP an alias, so I can use NP instead of writing out NumPy. That's why. Now, before I had an import random, but I'm going to use NumPy random. Why? Well, NumPy random can make random vectors all at once really fast in C. So if it gets really big, you know, and so I might as well use that. So from numpy.random, import a random, a name from this module, NumPy. NumPy is a module that's in a directory. It's got a module named random in it, which has a name random in it, which is a function, and import that as np_random. I did that in case I wanted to keep the Python random, which I had at first. This is something that ipython does. These are magics. And basically, this just runs a little Python program. And in this case, it imports matplotlib and NumPy all into the namespace. And it can take arguments. This argument means do the plotting in the notebook as opposed to popping up a separate window. In episode 2, I showed both. I showed it popping up a separate window. I had to switch to that window. The nice thing about the separate window is that it's interactive. You can, you know, if it's 3D, you can scroll around. So if it's 2D, it doesn't really matter quite as much, but, you know, it can. Depends what you're doing it for. So let me, I'm going to hold Control and hit Enter so that it'll run the cell but stay in the same cell, because I want to run it twice to show you something. Okay, see, populating the interactive namespace from NumPy and matplotlib, that's what pylab does. Now you can import pylab. It's a matplotlib thing. This pylab magic just does it all at once. If I run it again, Control Enter, oh, usually it gives a warning if you do it twice. Weird. Usually it says stopping the namespace. Okay, now I've changed create data sets. If you remember, it used to have order, and if the order was 4, basically you were getting an underlying curve that was y equals x to the 4. Well, now I pass in coefficients. Okay, so this function is meant to simulate real-world data that you would get where there was an underlying mathematical systematic shape to the data. So what I've done, just to remind everybody, is I'm calculating the data points that would be exactly along a curve, right? The curve that I'm using is something we wouldn't see in science, right? It's something we're trying to figure out. But just to make a model of the kind of data we'll look at later, we're going to look at real data. And we create these points that are exactly along that curve. And then I run through all those points and I randomize them. Okay, and I've added different kinds of randomization. right? And I've made it so that instead of just having y equals, x cubed, you can have y equals 3x cubed plus 2xy. In other words, you can have a polynomial. Okay, I'll also show fitting a sine wave. And the difference there will be that when we do the fits are polynomials. So a polynomial fitting can fit a set of data perfectly if there was no noise. I'll show you what I mean there. But it could never fit, even with no noise, a sine wave, except for a limited range. Okay. So when you do a fit like this, as InventiveHarvest said, you have to have a model in mind. Because if you just do a multi-order fit, well, that fit might be good at predicting where a future measurement will lie if it's within the interval where the measurements that were fitted were taken. But if you don't know the actual mathematics, then if you go outside what you've measured, you can't make predictions about what you will measure in that case. On the other hand, if you think the phenomena really is can be represented rather by a polynomial, then figuring out the polynomial for a limited set of data, if you had the order right, could do pretty good in extrapolating out to scales that you might not have measured at, and give you an idea of what to expect and how to build the device that might be able to measure it. All right, so now we're passing in the coefficients. As the random, the default is none. There's an argument called rand, and that's the rand factor is the way it was before, but now I've also done additive and stochastic. Right, rand scale is a number to say how much to factor by instead of always using 1. Oh, it doesn't fit now. See, I can do this. In Python, you can do a new line if you're within some kind of parentheses. So then we have the t range from -20 to 20. So let's go ahead and do 0 to 100 instead. 0 to 20, I guess. And then the step size, that's just the default. You can pass in, all of these sides are the default. This is a way you can tell Python, hey, I'm going to have something, I want to call it t range. The caller doesn't have to give me an argument, in which case this will be the argument, the default. Right. All right, so I've changed the word times to be x's. So this is a way to create a vector's worth of x's. So it's going to be 20. Really 0 to 19, 20 elements, but step size is 0.5, so it's going to be 40. Going right up to 19.5, and then 20 I don't think will be included, because when you have a range in Python, if you go, for example, range 5, that'll create a vector of integers 0, 1, 2, 3, and 4. 5 won't be in there, right, because 5 is the length. 0 counts. This is something you deal with in all programming languages, and Python is consistent about intervals being inclusive on the lower end and exclusive on the top. Right. I say RD equals a copy of D. I thought that was a problem before. Maybe not. Yeah, that must have been before. So this RD is going to be the randomized data. Oh yeah, I'm sorry. Okay, so the x's is this regular grid. Then I have coefficients. If the coefficients exist there, I create a polygon from the numpy function poly1d. And how's it going to know what poly1d is? Because that is not declared until later. But I did it already from NumPy import poly1d. So we better do that. From NumPy import poly1d. Okay, so then we'll run that. Okay, and then the data equals the source poly of those x's, right? So this is a polygon. This is a whole, 40 different values by default, and so D will be the, the y values, 40, a vector of 40 y values. If there are no coefficients, I do the same thing, but I calculate the sine wave. So we'll see that later. By passing coefficients none, I get a sine wave out of here. Okay, so then down here I do all that stuff I was talking about. If rand equals factor, that's the original one that I had, where I just multiplied the number by some random number times itself. So, it was basically could be plus or minus up to half of its own value. So the reason for that was because, I was dealing with lines, I was dealing with parabolas. If you get up there with a ninth order polynomial, then, it goes up to millions. And if you just have some sort of a constant value, it's hard to see. Okay, but then I did create this constant system. And then there's stochastic, where the data is all set to 0 and it's just random, right? And we'll fit that just to show what the polynomials are going to do when you fit it to data that we know is stochastic, at least, simulating random data. And then it returns those things. Okay, so let's see if that works. So that'll program that. So let's create some random data. That I've left in here. So this is a 0, 1, 2, 3, 4. So this is going to be x to the 4, and so on, polynomial. And I'm using rand equals additive, and step size equals 0.1, and random scale equals 0. So this won't be random. This will be it's randomized, but with the random scale 0, it will just be the data. So, and there's no coefficients. I didn't pass in the coefficients, so that's it doing the sine wave. So let's put this in. Let's go back to the default here. Coefs equals source coefs. Right. All right. So that's an x to the 4 thing from 0 to 20 goes up to 90,000. If we want it randomized, we can put in random scale in this case to be how much we want it plus or minus. Since we know it goes up to 90,000, let's say 10,000. You have to, so there you go. See, if I put this 50,000, it'll be scattered more, right? So let's just leave it at 50,000. All right. So here's the regular data underneath. Now we'll fit it. Okay, I've changed this from before there I had num terms, so this is the fit order. Let's see what it does when we leave it at 32. Why not? See, it's trying to follow all that random data. That's why we need to have a theory. We say, well, I think that this is the fit order is 4. Now it gets something pretty good. All right, now if we go up here and we lower the amount of randomness, okay, if you just look, well, I'll just go back down there. Okay, so that's a lot less randomness. Now this will allow the fit to be better, right? Because it's taking into account all of that scatter. And and that is the best guess, right? Mathematically provable best guess. So here's what it was like before. If I run it again, you can see that it's a lot closer, but you can still tell that the lines are different. Okay, now let's come down here to where we can look at the polynomial. Now, okay, I will go, InventiveHarvest was kind of curious how this works. So now when I teach how to format strings, I'm going to teach the proper modern way, but I'm used to old-fashioned format strings. So this %f is saying put a floating point there. Where does it get the floating point? Well, it's the first format thing, and here's the first thing it's given, so it'll put that in there and format it. This %d means it's an integer, and it'll put that in there. So I go through and I build this string that I happen to know is in a special language called LaTeX, and then I make this function coef to LaTeX. This calls coef to LaTeX with our coefficients that we have, both the source one and the fit, and then I'm able to display those two. So let's go ahead and display them. I've improved that a little bit. Okay, so here's the source poly. I did 0.5, 1, 2, 3, and 4, and this has, the first one's pretty good. This is, getting off by a factor of 4, then a factor of 25, then a factor of, huger and huger. That's as well as it can do. All right, so let's see what happens if I move this down. So let's put this back to 0 and see if it can fit that. Like I said, it should be able to fit that perfectly. 0. So I can't see the red line because the green line's perfectly over it. And then sure enough, it's fit that data perfectly. Okay, now what if, let's just put a little tiny bit of noise. Now remember, this thing goes up to 90,000 here. So I'm going to put in just a little bit of noise. The RAND scale, we'll just put in 10. Okay, and a scale that goes up to 90,000, so just a tiny little bit of noise. You can't even tell when you're looking at it. Let's see, there, I see the red line. Oh, because that's all that's shown here. I don't see the red line here. The green line's right on it visually, at least at that scale. Now let's look at the coefficients and see if they're the same. No, they're pretty damn close. Right, pretty damn close, but just 10 off out of 90,000 that goes up to. 10 off, plus or minus 5. And this is the result, it's off. So that's interesting. That's why we'll never know the real coefficients. Even if we did know something was order 4 and we're trying to figure out these coefficients from our data, we could get closer and closer. But if there's any randomness, which quantum mechanics and just general thermodynamics tells us, then it'll always be a little bit off. Let me go back up here and make this 0. 0 so it can fit perfect. And let's do a lot less elements. Let's make this step size, a tenth as many elements. Okay, so it's like that, right? Okay, so let's see if how it's going to do there. Can it figure it out when there's that few data? Yep. What if we go, now obviously at some point it's got to fail. Let's go 5. 5, it can't do 5. So is that enough to characterize that shape? No, not quite. Needs more than that. So let's just try one more and see. That's pretty few. Anyway, sorry. 2. Yeah, so that's enough. Now, I'm sure if you looked way out in the zeros, it's probably not exactly right. Because the fit can't be exactly perfect. It could just be way more than the precision we have here. So it's not going to be exactly right. But you get an idea of how, what's as rock solid of a fit as the math and the computer can even handle. All right, but you can figure this stuff out. Now, see, I'll show one more thing before I go on to the next. Since we have 0 information in the data, 0 mistakes, 0 randomness, let's put this back to 0.1 like we had, with 0 mistakes now. And we're going to fit the data but I'm going to go to the 33 like I did before. It doesn't like all that being so big. Let's just do 16 then. Okay, and remember there was zero noise, so what's it going to do here? All of those coefficients were zero. It still fit it. It knew this was all it needed because there was no noise. But, so I go back and put the 10 noise back in. Again, we have trouble telling the difference. Here it looks like it's fit, but it models all the way out to how far I told it. Because the noise makes it think that it needs to model better. All right, so the final thing I'll show is creating a sine wave. Now, if the coefficients are none, which they are by default, but I'll just set them there, then we get a sine wave. Now, the scale of 10 is pretty bad for a sine wave since it only goes up to 1. So let's say 3. There we go. All right. Right. So there's that. Here's the fit. Oh, it does pretty good with 16, right? So look down here, these coefficients are not right. Sorry, those coefficients are not right anymore because I'm not doing that. I'm doing the sine wave. So here's the polygon that it comes up with. And even though if I do an x to the 16, it'll look nothing like that. You know, it's just going to go up like the half a parabola. With all of those and shifted, it can make it go up and down that well. If I do, again, if I do just 1, I'm going to get a line. That angle is not so much the randomness, but because of where I start and stop. 4, see, it's going to shift it over. Start to get pretty good at even only 9 within that range. Okay. So one thing I was going to show, so if you wanted to do a linear thing with this InventiveHarvest, then it's the coefficients you pass in. So if I did the coefficients of 3 and 0.07 or 567, then I'm going to get, and I pass those in, then I get a line, right? So let's say the scale is plus or minus 5, I don't know, right? The factoring factor type is it gets bigger as you go out, and you probably want to use it. Then the scale is multiplied, so you want to go out, you know. So it gets broader as it goes out, right? As it fans out in negative or positive quadrants, right? So so I like this additive one, and then you want to do, it's more of an absolute scale. So oops, that's 0.2. Let's do. Okay, so let's say you had that, and then we're going to try to fit that. Well, if you fit it like that, yeah. So I'm kind of curious. So if you fit it like that, let's see. The if we fit it like that, what was the coefficients again? 3 and 0.567, 0.0567. So if we fit it like that, what did we get out? Goes up to 9. Yeah, not 3 and 0.507. Okay, but let's go back and do it with fit it with a single order, since we know it's linear. So that does pretty good, and not bad, not bad. It's got that slope component pretty good. So So anyway, there we go. I hope that helps. Now, InventiveHarvest, I saw you try to do some vector stuff in sympy, and it works totally different. So we'd have to figure out how to do that if you really want to use sympy to evaluate vector equations. It seems to be that it has some features like that. So all right, that will call an end to this episode, and I'll see you next time. Cheers.